Okay, just working through the examples on pages 4, 5, and 6 to go with topic 1. Okay, so first one here, just a conversion. A photon has an energy of 1.5 electron volts. What is its energy in joules? So just the skill of converting units, because all an electron volt is a unit of energy. Okay, I want to have joules, and I'm converting with electron volts, so I want those to cancel out, right? Now I just got to think, okay, well, 1 electron volt is the same as a very small number of joules. This one, a 0.18 zeros, and then a 1 and a 6. Okay, what is its speed? Trick question. It's a photon. It's light. It's a packet of light, sure, but it's still light. So what's its speed? C, right? Okay, don't fall for that one. No calculations required there. Now, what's its wavelength? Okay, here we're going to have to apply Planck's formula, right? So E equals hc over lambda. Its energy is inversely proportional to its wavelength. I kind of think of it as a wavelength like this, right? That's jiggling a lot. That's high energy, whereas this guy is pretty chill, right? Low energy wave. Okay, so manipulating that for lambda and plugging in our constants. Whoops, I never actually got an answer here. Cancel out the electron volts. Okay, that's the energy in joules, which is what goes here. Don't use the electron volts. And if you're being a good physics student and always checking your units, or at least when you're getting a new equation, which you should be checking your units, okay, you would see why, aha, I can't use electron volts here because then joules wouldn't cancel with joules, right? Which we need it to because we also need seconds to cancel with seconds, leaving us with meters, the unit of wavelengths. Very good. So we're feeling good about this now. Okay, I got 828 nanometers. What is the frequency of a light wave with that wavelength? So we could just use our universal wave equation. We just found lambda, so we could use, right, that would work. We just got a new equation and we just calculated lambda. What if that's wrong? Let's just take our new equation for a test spin, and at the same time, it'll allow us to only use the numbers they gave us. So again, we're dealing with one photon here, one quantum of energy, so that n is really there, but there's just one photon, so it's okay. So just solving and plugging in, and then joules cancel, joules cancel. I have 1 over seconds, which is a hertz, the unit of frequency. Feeling good. All right, what's its period? We haven't talked much about the period of EMR, but it's the same as when you did it in physics 20, right? Frequency is how many oscillations per second. Period is how many seconds per oscillation. So how long does it take this EMR for the electric field to go from one orientation to the opposite orientation and back again, right? One full wavelength. So it's just the inverse of the frequency. Oscillations per second versus seconds per oscillation. Putting in my extra sig digs there that I really should have written down, but it's almost June. Give me a break. And what are the units of period? Well, I have 1 over hertz, which is 1 over inverse seconds, right? 1 over seconds. So just like they should be, because it's seconds per oscillation, that's how long I'm finding it takes for this light to complete an oscillation. Makes sense, right? Light is oscillating very quickly. Electric fields oscillate fast, right? Even radio does it really quick. What's the type? Okay, you can be a frequency person. I've never understood frequency people. I find it really hard to pull meaning out of that, though. However, wavelengths, I have a much easier time imagining. And a big part of that is that I know the visible light is from 350 blue to 700 red nanometers. Okay, so when I see 828 nanometers, okay, that's a little bit above 700. So that is outside of the visible range, and it's outside on the red side of things. So this is pretty close though to visible. This is definitely going to be infrared. Okay, another example here. So recall that X-rays are created by stopping high energy electrons, right? Stopping is an acceleration. So you give them a lot of energy, that means they're moving quick. Stop them, that's a big acceleration. Big acceleration, high energy, high frequency, small wavelength EMR produced like X-rays. Okay, so this is serving as a subtle reminder that you do generally need to be able to describe how different forms of EMR can be produced. Okay, now if electrons are accelerated from rest by a potential difference of 2000 volts and directed at a lead block, describe the formation of the X-rays using proper physics principles. So really all we need to think about here is Number 5, the conservation of energy, right? What do we have? These electrons, if we put them in an electric field where there's some potential difference, right? Well, now I just said it, potential difference. They have some potential energy, right? There's a difference in potential energy from where they are to somewhere else. So they have electric potential energy. As we allow them to accelerate through that, we allow that potential to live up to its potential and become kinetic. Then the electrons get stopped, but is energy destroyed? No, right? Where does it go? Into EMR energy of the X-rays. All right, and it wants us to find the X-rays wavelength. So to find the X-rays wavelength, what do we need to know using our new formulas, right? Well, we have E equals hc over lambda. H and C are constants, no problem. We're looking for lambda. So if we had the energy, this would be solved. Do we know the energy of the X-rays? No. Can we figure it out using physics principle number 5? You bet, right? That was the idea here. We know where it all came from, so let's go get it. Find the energy. So really, the energy that becomes the EMR is the kinetic energy of the electrons. But the kinetic energy will be the same as the electric potential that it got accelerated through, right? So we can just find that and we're done. If you wanted along the way, you could find their kinetic energy like we would back in chapter 11, but why bother now? Let's just say the energy of the X-rays equals the kinetic energy the electrons had, which is equal to the change in energy caused by the potential difference, the charge, times the potential difference, which again is joules per coulomb. So per coulomb of charge, how many joules of energy would it gain or lose depending which way you move it through this voltage? And they are electrons, so their charge is elementary charge. The voltage was 2000 volts. Okay, so that's how much potential energy these electrons had at the beginning. And therefore, it's how much kinetic energy they had at the end. And therefore, it's how much kinetic energy is going to be turned into EMR energy in the X-rays, right? Notice, we're still doing physics 20 stuff here. Conservation of energy. The energy is just starting to get weirder. So putting in the new equation, manipulating it for lambda, and now we will plug in. I got that their wavelength was, okay, good way to check your work here too, right? Remember, you do have to know roughly the MR spectrum. I know that that's X-rays, okay? Again, visible light is kind of in the middle of the hundreds of nanometers. Ultraviolet is from the low hundreds down to about 10 nanometers, and X-rays is beyond that. So this is definitely, so this is about 0.6 nanometers. This is definitely an X-ray. Feeling good about that answer because I know my spectrum. So should you. All right, let's do a calculation here that kind of makes us think a little bit more about these packets of energy. We've just kind of been throwing this idea around. So if Planck is correct and light comes in these packets of energy called quanta, again, it's kind of weird to say Planck is correct because remember, he didn't think this was a physical actuality, right? This was a math trick. Planck was the first guy to tell you that I don't think this is real. Okay, it just makes the math work. How many would be emitted by a 1.5 milliwatt laser each second if the laser produced light with a frequency of 4.75 times 10 to the 14 hertz? So that's frequency, watts. We haven't seen that since physics 20, or at least not much. That's power. What's power? Again, just energy per time, right? So honestly, when I see 1.5 milliwatts, I don't even think about watts or anything. I think, okay, every second this thing releases 1.5 joules of energy. I right away turn it into energies in my head. So power equals energy over time, right? So each second, so we'll just say time is equal to 1 second then, the amount of energy this thing puts out is how many joules it's putting out per second times how many seconds have gone by, right? Well, that makes sense. But that's not what this question asked. It asked how many of these little weird packets come out. So usually we could kind of do this in one step, but let's kind of go ahead and do this in 2 steps since we're just kind of easing our way in. So it puts out 1.5 times 10 to the minus 3 joules per second. And we're saying how much does it do each second? So 1 second. So the total energy, not surprisingly, is, right, if it's putting out 1.5 millijoules every second, then in 1 second it puts out 1.5 millijoules. Nothing earth-shattering there. That is the total amount of energy it's going to put out. But this question is saying, okay, great, that's the total energy. Don't forget these packets of energy, right? So it's a little bit like pixels on your phone. overall, yeah, it looks continuous. It looks like one big picture. But if you zoom in far enough, your screen is made up of little pixels, right? It's pixelated, it's quantized. Okay. So the math trick that worked was to then assume that this energy was not continuous, not infinitely divisible, and there was some smallest amount. So this total energy was made up of tons of these little packets. Okay, you can have as many packets as you want, you just can't have half of them. So let's see, how many of these little packets of energy would it take to make this much total energy? So we're looking for the energy per photon here, right? And so remember, this is the energy of a packet, h times the frequency. And so if we want to know the total energy, we'll say, okay, there's the energy of one packet, times it by the number of packets to get the total, right? Okay, so then if we want to know the number of photons, now we've got all that stuff. Plug it in. And we should be getting a dimensionless quality here, something with no units, right? Photons, I guess you could say the unit is photons, but it shouldn't come out of our standard international units, right? It shouldn't come out of these guys here that we have plugged in. So joules over joules, good. Hertz times seconds, well, remember, hertz are just inverse seconds, so inverse seconds times seconds is just 1. Very good. I got that to get that amount of energy, you would need 4.76 times 10 to the power of 15 photons. So that is about almost 5 quadrillion photons. Can't see me, but I just put my pinky to the corner of my mouth. Okay. So, and that's for a little laser, a 1.5 milliwatt laser. That's not even that good of a laser. Okay. So photons, very small packets of energy, yes, but still the minimum amount, right? Again, your phone screen becomes a good analogy because from far away, there's no way to tell at all that your phone is made up of little tiny quantized things. However, if you zoom in really, really, really far, you can see the individual little quantized pixels that make up the seemingly continuous image that is not continuous. So an X-ray is used for 20 seconds in a dentist office. The person's teeth absorbed 1 millijoule of energy during this time. If the teeth absorbed that many photons, what is the wavelength of the X-rays? So this is definitely what is the wavelength of the X-rays? Okay, so what do we got? That is N. Oh, we've got the total energy. We want to know wavelength. Okay, so the total energy is going to be N, the number of photons, times the energy per photon again, which is HF, or that one, right? This one will be useful to us here. It just depends whether they give you the frequency or the wavelength, which one you would rather use. Okay, so they gave us the wavelength. Let's use this guy. So it's saying if they absorb that many photons and that represented that much energy, what must be the wavelength of every photon? Okay, so just rearranging for wavelength, and we're ready to plug in. Used a whole bunch. Dimensionless for photons, right? Let's do a quick unit check while we're here. Joules over joules, okay? Seconds times 1 over seconds. Very good, we got meters. That's what we should get for lambda, so we're feeling good. But I got that the wavelength was 1.2 times 10 to the negative 8 meters, or about 12 nanometers, right? Okay, good. That's definitely in the higher range of X-ray rays, but it's still safely within the X-rays. So feeling pretty good about that answer there. So again, interpret your answers. Think about what it's saying physically, right? Never just blindly write down a number. That is the wavelength of every photon if the total amount of energy absorbed when you absorb that many photons is 1 millijoule. Okay, a photon has 27 nano electron volts of energy. What type of photon is it? First things first, as soon as you see that, okay, kind of like kilometers per hour in physics 20, you should probably think about converting it. And we're going to have to here because we're going to have to use Planck's constant. Now that you've seen a couple energies in electron volts, what do you think this is? Do you think this is a high energy wave or a low energy wave? Do you think it's closer to radio or closer to gamma? Okay, I'm going to let that sit. See what we get in the end. So to figure it out, we should look at the wavelength, right? That's always easiest for me. So manipulating and plugging in. I got that the wavelength was 46 meters. Okay. Yes, EMR that big exists. EMR bigger than that exists. There's EMR that's really, there's no limit to how big the EMR can be, right? However, as soon as you get above 1 meter for the wavelength, you are safely into Radio. Definitely radio waves. How do we produce radio waves? Do you remember? Maybe I'll ask you this. How do you receive your radio waves? It's the same sort of process. To produce a radio wave, we allow an electron to oscillate in the wire, and that acceleration produces long wavelength radio waves. Okay, here's one from an old diploma. So chlorophyll in plants absorbs photons of electromagnetic radiation and then converts them into chemical potential energy. Once again, the coolest things in science always come down to physics. Chlorophyll A is one of the main types of chlorophyll. Okay, the graph below shows the relationship between the absorption of photons by chlorophyll A and the wavelength of the photons striking the plants. So in other words, when a photon hits it, how well the plant will absorb that photon relate to the wavelength of the photon. So in other words, peak here means chlorophyll A is really good at absorbing that wavelength, right? Peak here, very good at that wavelength. Not so much here in the middle. So produce the maximum rate of photon emission by chlorophyll, photons should have an energy of, well, the maximum rate of absorption seems to happen right about, right? This peak is the highest one, so right about here, which is 620, 40, 60, 660 nanometers. So what's the energy it should have to best get absorbed? Well, what's the energy associated with that wavelength? Because clearly it likes this wavelength. Again, I'm not forgetting the n, it's just the n is 1 here because we're talking about one photon. It's saying what energy should a photon have? So just plugging in. Check the units. Meters cancel, seconds cancel. This time we're left with joules, just like we should be. I got 3.01 times 10 to the negative 19 joules, which would be a little less than 2 electron volts, right? Because 1.6 times 10 to the negative 19 is an electron volt. Okay, what produces better rates of photon absorption, infrared or ultraviolet light? So this requires knowing your EMR spectrum, right? So what color is 660 nanometers? Well, I chose it appropriately, okay? That's red, right? From about 600 to about 700 is all red. As we go this way, the wavelengths get bluer. So this actually only shows the visible spectrum. It doesn't even go off of it, but you can kind of see, right? Now, truthfully, if we want to be really careful, we should see more, but you can probably extrapolate from this graph and say, looks like in the infrared, which is slightly bigger wavelengths than red, slightly lower energies than red, right? Over here, right? That's infrared. What's down over here? Well, the other one they asked us about, the ultraviolet. So violet is right here, even a little bit over here would still usually be considered violet. It's kind of off the graph this way. Just going to redraw that because it looks like I'm trying to say it's big. There's a lot of absorption. All I mean is that that's where it is. So how about I go like that? Okay. So you can tell from looking at the graph, right? Ultraviolet looks like it's still, there's going to be some absorbed. Infrared, definitely not. Again, because, right, graph just looks to drop off right away to 0. Okay, use this diagram to explain why plants appear green. Well, helps to know the wavelengths, but at the same time, if you can recognize that this is the visible spectrum, Roy, G, Biv, right? Right in the middle. ROY, and then green, and then BIV, okay? So what's the middle of the graph look like? How's that look for absorption? Not great, right? So green, I usually think of as in the 500s-ish, right? So if plants are clearly not doing a great job of absorbing green photons, what are they doing with them? Well, they're reflecting off, right? And if they're reflecting off, where can they go? Into our eyes, right? Why don't plants appear very red? At least most plants, they're absorbing all the red light. They don't appear very purple, at least most of them, because they're absorbing the purple light. However, a lot of them appear green because this chlorophyll A that so many of them have does not absorb that green light. So it bounces off of them and into our eyes. And so we say, hey, those plants are green because green light's bouncing off of them. Those wavelengths of photons are bouncing off of them into our eyes. Right? So if they're not absorbing the green light, they must be reflecting it. Since seeing something is just having light bounce off of it to your eyes, if the green light is what's bouncing off of it to your eyes, it appears green. Okay, and that wraps up the examples video for this topic 1. So if you're looking for practice to do on your own, you can look for the questions that go with this in the Google Classroom or agenda.